Across the rust-colored plains of Mars, beneath layers of ancient regolith and frozen time, lies a discovery that has captivated humanity's imagination and sparked a trillion-dollar dream. When NASA announced the detection of massive ice deposits hidden beneath the Martian surface, headlines blazed across the world. Water on Mars. Colony survival secured. The key to Mars settlement found. Scientists stood before cameras, showing radar images of vast frozen reservoirs stretching across the northern and southern latitudes. Political leaders spoke of Mars as the next frontier. Entrepreneurs unveiled timelines for self-sustaining colonies, their presentations glowing with artists' renderings of habitats surrounded by greenhouses, drinking water flowing freely, rockets refueling for journeys deeper into space, all powered by ice waiting just beneath our feet. The vision was intoxicating. Endless water, the most precious resource in space, simply buried beneath the surface like a cosmic gift. No need to haul it from Earth at thousands of dollars per kilogram. Just land, drill, melt, and survive. The ice would give us drinking water, oxygen to breathe, hydrogen for fuel. Mars itself would provide everything needed to transform a barren world into humanity's second home. The promise felt so close, so tangible, that it reshaped our collective dream of becoming a multi-planetary species. But tonight, as we drift through the science of this extraordinary discovery, we will uncover a truth that most never consider. Finding ice on Mars and actually using it to sustain a colony are separated not by months or years of engineering, but by a chasm of challenges so profound they may redefine everything we thought we knew about Mars settlement. The ice is real. The deposits are vast, yet between discovery and survival lies a landscape of toxic chemistry, impossible depths, crushing energy costs, and engineering puzzles that have no easy solutions. If you have ever wondered why the Mars colony timeline keeps shifting, why the confident predictions grow quieter with each passing year, this journey will illuminate the beautiful, uncomfortable gap between vision and reality. Please like and subscribe as we explore not just what we found on Mars, but what it truly means to extract life from a frozen alien world. Now settle in, let your curiosity deepen, and let us descend gently beneath the surface of the trillion-dollar illusion, where science, dreams, and physics collide in the Martian dark. Before we could debate whether Mars ice would save a colony, we first had to find it. The search for water on Mars is not a recent fascination, but a century-long detective story written in spectral lines, radar echoes, and fleeting glimpses through telescopes, pointed at a rust-colored world that has captivated humanity since we first turned our eyes skyward. In the early 1900s, astronomers observed Mars through primitive instruments, noting white caps at its poles that expanded and contracted with the Martian seasons. Were they frozen water or frozen carbon dioxide? The question lingered for decades, unanswered, tantalizing. Some speculated about ancient oceans carved into dry riverbeds. Others saw only wishful thinking projected onto barren rock. Mars remained silent, keeping its secrets locked beneath layers of dust and time. The first true confirmation came not from grand pronouncements, but from patient observation. The Viking landers in 1976 detected water vapor in Mars's atmosphere, trace amounts that hinted at reservoirs hidden somewhere below. Orbiting spacecraft measured hydrogen signatures in the soil, indirect evidence that ice might exist just beneath the surface. Yet these were shadows of proof, reflections in a cosmic mirror. We knew water had once flowed on Mars, but did any remain? Then came 2008, and with it, a moment of extraordinary scientific poetry. NASA's Phoenix lander touched down in the northern Arctic plains of Mars, a region chosen specifically because orbital instruments suggested ice lay close to the surface. On Sol 20 of its mission, Phoenix's robotic arm scraped away the rusty topsoil, revealing bright white material underneath. Scientists watched with held breath as cameras photographed the same patch of ground over subsequent Martian days. The white substance slowly disappeared, vanishing directly into vapor without melting. Sublimation, the unmistakable signature of water ice exposed to Mars' thin atmosphere. It was a profound moment, not for its complexity, but for its simplicity. Humanity had finally, definitively, touched water ice on another world. Not through inference or speculation, but by watching it evaporate before our eyes, frame by frame, like a time-lapse of cosmic confirmation. Phoenix had answered a question centuries in the making. Yes, water ice exists on Mars, accessible, tangible, real. Yet the Phoenix discovery was only the beginning. What lay beneath represented something far more significant than a patch of frozen ground in the Arctic. While Phoenix scraped at centimeters of depth, orbiting spacecraft peered far deeper, using radar instruments that could penetrate Mars's surface and map structures hidden below. SHARAD, the shallow radar instrument aboard NASA's Mars Reconnaissance Orbiter, and MARSIS, the Mars Advanced Radar for Subsurface and Ionosphere, sounding on ESA's Mars Express, began revealing a hidden world. Massive sheets of ice, hundreds of meters thick, buried beneath protective layers of dust and rock. These were not scattered deposits, but glacial reservoirs, frozen remnants of Mars' wetter past, preserved like fossils in stone. The radar data painted a picture that stunned the scientific community. Mid-latitude regions, far from the polar caps, harbored enormous ice deposits. Not on the surface where they could be easily accessed, but buried under meters, sometimes tens of meters, of protective regolith. The ice exists in a delicate equilibrium, shielded from the sun's radiation and the planet's thin atmosphere, both of which would cause exposed ice to sublimate away, as Phoenix had witnessed. Mars guards its water jealously, hiding it beneath veils of dust that have accumulated over millions of years. Then, in 2018, came perhaps the most visually striking discovery of all. Scientists analyzing high-resolution images and topographic data identified nearly vertical cliffs of exposed ice in 8 locations scattered across Mars' mid-latitudes, concentrated in a region called Utopia Planitia. These were not gentle slopes or hidden deposits requiring excavation. These were scarps, sheer walls of ice more than 100 meters tall, exposed by erosion where the protective dust layer had worn away. The ice glowed blue-white in enhanced color images, pure frozen water, standing like monuments to Mars's ancient climate. Before we continue deeper into this story, I'd like to pause for a moment and invite you to share something. Would you comment below and let me know where you're watching from and what time it is? Whether you're drifting towards sleep in a quiet room, listening during a long night shift, or starting your day on the other side of the world, I'm curious about this community we're building together. There's something beautiful about the idea that we're all contemplating Mars, scattered across Earth, united by curiosity about another world. The discovery of these ice cliffs represented both triumph and complication. Yes, here was accessible ice, exposed and waiting. No drilling or excavation required. Yet the cliffs existed in locations carefully selected by geology and erosion, not by human convenience. They were far from potential landing sites, situated at latitudes and elevations that complicated mission planning. The ice was there, undeniably present, but reaching it would require careful consideration of terrain, climate, and engineering constraints we'll explore shortly. These discoveries transformed our understanding of Mars from a dry desert world to a planet where water, in frozen form, exists in abundance. The scientific achievement cannot be understated. Generations of planetary scientists had theorized, hypothesized, and searched. Now we knew. Mars holds water ice near its surface, in its subsurface, locked in its polar caps, and exposed in rare cliff faces where erosion has revealed ancient glaciers preserved beneath protective dust. Yet discovery and accessibility are not the same thing. Finding ice on Mars is one achievement. Using that ice to sustain a human colony is another question entirely, one that bridges the gap between planetary science and engineering reality. The ice exists, yes, but where it exists, how deep it lies, what contaminants it contains, and what it would take to extract, purify, and utilize it, these questions transform celebration into calculation. The story of finding Mars ice is ultimately a story about patience and persistence, about looking at a distant world and refusing to accept mystery as final answer. We found the ice through decades of observation, ingenious instrumentation, and the courage to send robots millions of miles to scrape at alien soil. The discovery is real. Discovery, the ice is waiting. What comes next is where dreams meet the unforgiving mathematics of survival in a place where nothing comes easily, and every resource must be earned through careful planning, immense energy, and engineering that pushes the boundaries of what we know how to build. Mars reveals itself slowly to those who study its surface. From orbit, our spacecraft maps the red planet in extraordinary detail, pixel by pixel, building a portrait of a world both familiar and alien. The data flows in streams of electromagnetic whispers, each signal carrying information about elevation, temperature, composition, and hidden beneath the rust-colored soil, the presence of water ice. Yet, as this picture becomes clearer, we encounter a profound geographical irony, one that transforms the promise of Martian ice into a puzzle of location and access. The ice is there. The instruments do not lie. Radar penetrates the surface, revealing deposits that shimmer in the data like buried treasure. But where exactly is this ice? And more importantly, where can we safely land to reach it? These two questions do not share the same answer. In fact, they reveal a cruel cosmic joke that has troubled mission planners since the first detailed ice maps were compiled. The richest concentrations of accessible water ice exist primarily in the polar regions and high latitudes of Mars, predominantly above 60 degrees north and south. Here, near the planet's caps, ice exists in abundance, sometimes mere centimeters below the surface, sometimes exposed directly to the thin atmosphere. The Phoenix lander confirmed this in 2008 when it touched down at 68 degrees north and scraped away a shallow layer of soil to reveal pure water ice gleaming in the Martian sunlight. The ice was so close, so accessible, that sublimation was visible in the spacecraft's own photographs, the ice transforming from solid to vapor before our cameras over the course of Martian days. This discovery was scientifically triumphant, but operationally bittersweet. Yes, the ice was there, abundant and near the surface. But landing at 68 degrees north is an endeavor that pushes the boundaries of what is possible, and living there permanently borders on the impossible with current technology. The constraints of landing on Mars are unforgiving. Every mission must balance a complex matrix of requirements that rarely align with human desires. First, there is the matter of terrain. A spacecraft descending through Mars's thin atmosphere needs flat, relatively obstacle-free ground. Boulders, steep slopes, and crater walls are potential death sentences during touchdown. The landing ellipse, the area where a spacecraft might actually touch down, given the uncertainties of atmospheric entry, can span dozens of kilometers. Every square meter within that ellipse must be survivable. Then there is elevation. Mars's atmosphere is already desperately thin, just 1% the density of Earth's. At higher elevations, it becomes even thinner, reducing the effectiveness of parachute braking systems. Most successful landing sites have been at lower elevations, where the atmosphere, though still tenuous, provides just enough resistance to slow a descending craft. The deepest basins and lowest plains become preferred targets, not for their scientific interest alone, but for their atmospheric density measured in fractions of a percent. Temperature and solar power introduce yet another constraint. Mars is a cold world, with average surface temperatures around -80 degrees Fahrenheit. But the polar regions and high latitudes experience far more extreme conditions. Winters plunge into darkness for extended periods. Temperatures drop so low that carbon dioxide itself freezes out of the atmosphere, creating seasonal caps of dry ice that advance and retreat with the Martian year. For a human settlement dependent on solar panels for energy, these regions present a challenge bordering on impossibility. The sun hangs low on the horizon even during summer, and winter brings twilight that stretches for months. Equatorial and mid-latitude regions, by contrast, offer more moderate temperatures, consistent sunlight, and the kind of environment where human technology can operate with greater reliability. These are the regions where rovers have explored most extensively, where the skies are clearer and dust storms, though still formidable, are somewhat less catastrophic. These are the places we would prefer to land. These are the places we would prefer to build. And yet, equatorial Mars is comparatively ice-poor. The water that once flowed across this world has retreated, locked away at higher latitudes, or buried at depths that make access extraordinarily difficult. The geographical distribution of ice follows a gradient that becomes steeper as one moves towards the equator. Surface ice cannot exist in the warmer regions. It sublimates away under the faint but persistent touch of sunlight. Any ice that remains must be buried deeper, insulated by layers of regolith and dust. This is the cruel irony that confronts every colony plan. The safe landing zones, the regions with adequate solar power, the areas where temperatures are least hostile. These places overlap only marginally with the ice-rich zones. It is as if Mars itself is presenting a test, offering water in locations that are difficult to reach and difficult to inhabit, while the comfortable regions remain parched. Mid-latitude regions between 30 and 60 degrees represent a compromise that satisfies no one completely. Orbital observations have revealed ice deposits in these zones, buried beneath layers of soil. The Mars Reconnaissance Orbiter detected subsurface ice at various mid-latitude sites, sometimes as shallow as 1 meter below the surface. This sounds promising until one considers the operational reality. Even 1 meter of Martian regolith represents a significant excavation challenge. The soil must be cleared, moved, and processed. Equipment must withstand abrasive dust and temperature cycles. And all of this must occur in quantities sufficient to support not a single experiment, but an entire colony's water needs, day after day, year after year. The depth of mid-latitude ice varies dramatically across small distances. One location might have ice at 1 meter depth. A site just kilometers away might require digging 3 times as deep. without extensive ground-penetrating surveys, which themselves require landing and deploying equipment. Selecting a colony site becomes an exercise in calculated risk. Landing site selection has thus become a multivariable optimization nightmare. Mission planners must weigh terrain safety against ice proximity, solar power availability against temperature extremes, atmospheric density against latitude, scientific interest against operational feasibility. Each variable constrains the others. Optimize for one factor, and you compromise another. Search for the perfect landing site, and you may find that it does not exist. Computer models run thousands of simulations, adjusting parameters by tiny increments, seeking some combination of coordinates where all requirements meet at an acceptable threshold. But acceptable is not ideal, and threshold is not comfortable. Every proposed colony location is a compromise with Mars, a negotiation between what we need and what the planet offers. The geography problem extends beyond mere location. It touches on fundamental questions of strategy. Should colonies be placed near ice, accepting higher risks and greater energy demands? Should we land in safer zones and transport ice from distant locations, adding logistical complexity? Or should we develop entirely new landing technologies capable of reaching high-latitude sites, systems that do not yet exist outside theoretical papers? Mars does not withhold its water out of malice. It simply arranged its resources according to planetary physics, thermal dynamics, and billions of years of atmospheric evolution. The ice went where conditions allowed it to survive. Those conditions are not the same conditions that favor human habitation. Understanding this is not about finding fault with Mars or with our plans. It is about accepting that the distance between discovery and utilization is often measured not in meters of soil, but in the gap between where resources are and where we can safely be. As we study the maps glowing on our screens, each potential landing site marked with notation and probability, we recognize that the geography problem is really a question about commitment. How much are we willing to adapt to reach the water? How far are we willing to go? We have found ice on Mars. The orbiters have confirmed it. The landers have sensed it. The instruments have measured its presence beneath the rusty surface. But there is a difference between knowing ice exists and being able to reach it. A profound difference that transforms hope into challenge and possibility into paradox. The ice of Mars is not waiting at the surface like snow on a winter morning. It is buried, entombed beneath layers of regolith and rock, hidden in depths that vary wildly across the planet's terrain. In some locations, ice lies tantalizingly close, perhaps 1 meter beneath our feet. In others, it rests 100 meters down, or deeper still, locked away in geological vaults that would require industrial excavation to breach. The question is not whether Mars has water. The question is whether we can dig deep enough to claim it. Mars regolith is unlike any soil found on Earth. It is not the soft loam of a garden bed or the sandy drift of a desert dune. It is a mixture of sharp-edged particles, pulverized by billions of years of meteor impacts and cosmic weathering. Mixed within these particles are rocks, boulders, and a substance that makes the entire challenge more complex: perchlorates. These are toxic chlorine compounds that permeate Martian soil, created by ultraviolet radiation, breaking down minerals over eons. The regolith is not merely difficult to dig through. It is chemically hostile, electrically charged, and in many regions, compacted to a density that rivals concrete. Earth's soil has been softened by water, by life, by the ceaseless churning of biological processes. Mars has known none of these mercies. Its surface is hard, ancient, and unyielding. To understand the depth dilemma, is to imagine standing on Mars with a shovel in hand, looking down at ground that hides its treasure like a miser hoarding gold. In the mid-latitudes, where some of the most accessible ice deposits have been detected, the ice typically begins 1 to 3 meters beneath the surface. This seems manageable, almost inviting. A few meters of digging, and water awaits. But digging on Mars is not the same as digging on Earth. The lower gravity, just 38% of Earth's, means that tools designed for terrestrial excavation behave differently. A pickaxe swings with less force. A drill bit encounters resistance without the gravitational weight to drive it deeper. Every motion requires recalibration. Every tool must be redesigned for a world where physics operates at a different tempo. And this assumes the ice is only a few meters down. In many regions, particularly closer to the equator where landing sites might be more favorable for solar power and thermal regulation, ice retreats deeper into the subsurface. 10 meters, 30 meters, sometimes more than 100 meters beneath the regolith. At these depths, excavation transitions from a challenge to an engineering nightmare. On Earth, mining operations at such depths require massive machinery. Excavators, bulldozers, drilling rigs that weigh hundreds of tons and consume staggering amounts of energy. Transporting such equipment to Mars becomes a puzzle of payload limits and launch costs. Every kilogram sent to Mars costs thousands of dollars. Every piece of heavy machinery adds exponentially to mission complexity. Current spacecraft payload capacities are measured in tons, not hundreds of tons. The Mars rovers that have successfully landed, Curiosity, Perseverance, weigh roughly 1 ton each. The equipment they carry is miniaturized, optimized for scientific investigation rather than industrial excavation. Scaling up to mining operations would require not just larger equipment, but fundamentally different infrastructure. Landing systems capable of delivering heavy loads without destroying them. Power systems robust enough to run excavation machinery for hours or days at a time. And all of this must function autonomously or with minimal human oversight, at least in the early phases of any colony attempt. The energy requirements compound the problem in ways that are easy to overlook. Excavating frozen ground requires breaking through not just soil and rock, but ice itself, which at Martian temperatures can be as hard as stone. On Earth, mining operations use diesel-powered machinery, hydraulic systems, and the abundant availability of replacement parts and repair technicians. On Mars, energy must come from solar panels during limited daylight hours, or from nuclear reactors that add their own mass and complexity to the mission. Every joule spent digging is a joule not available for life support, habitat heating, or scientific research. The energy budget of a Mars colony is finite and unforgiving. Digging for ice is not just physically demanding. It is energetically expensive in ways that ripple through every other system. There are locations on Mars where the ice comes closer to the surface, where the depth dilemma eases slightly. Spacecraft like the Mars Reconnaissance Orbiter have identified sites where ice is exposed on crater walls or slopes, sometimes visible as bright blue-white streaks against the red terrain. These are tantalizing targets, places where excavation might be measured in centimeters rather than meters. Yet these locations carry their own complications. Steep slopes are difficult to land on and dangerous to work around. Crater walls may be unstable, prone to collapse or landslides triggered by the low-gravity environment. And exposed ice, while accessible, sublimates rapidly in the thin Martian atmosphere, meaning it must be harvested quickly or covered to prevent loss. Accessibility and stability are often inversely related. The easiest ice to reach may be the hardest to work with safely. As we consider the depth dilemma, we must also acknowledge the psychological dimension. For planners and engineers on Earth, designing excavation systems is an abstract challenge, a problem to be solved with calculations and simulations. But for the first humans standing on Mars, looking at meters of rock and dust separating them from water, the reality will be visceral. The cold, the isolation, the relentless physical effort required to dig through ground that resists every motion. Unlike the romantic image of explorers discovering a frozen lake or drilling into a pristine ice sheet, Martian water extraction will be industrial, grinding, repetitive work performed in spacesuits, under time pressure, with the constant awareness that failure means thirst, or worse. And yet, the depth dilemma is not insurmountable. It is a challenge that can be met with ingenuity, with robotic assistance, with technologies we are only beginning to develop. Lightweight drilling systems that use ultrasonic vibration rather than brute force. Robotic excavators powered by small nuclear reactors. Thermal lances that melt through regolith and ice simultaneously, creating access tunnels that human crews can descend into. The solutions exist in theory, sketched in research papers, and tested in laboratories designed to simulate Martian conditions. What remains uncertain is whether they can be deployed at scale, maintained over years, and integrated into a functional colony infrastructure. The depth dilemma is a reminder that Mars does not give up its resources easily. Every advantage comes with a corresponding challenge. Every discovery reveals a new layer of complexity beneath. The ice is there, vast and ancient, holding the promise of water, oxygen, and life support. But between that promise and its fulfillment lies meters of toxic, compacted regolith, and the enormous task of moving it aside. In this buried treasure, we find not just water, but a test of human determination, a question posed by the planet itself. How badly do we want to stay? And how much are we willing to dig to prove it? Finding ice on Mars sounds like the end of the story. In reality, it's the prologue to an engineering saga that has barely begun. On Earth, water is something we tap. We drill a well, drop a pump, and let gravity and pressure do half the work for us. On Mars, there is no easy tap, no aquifer waiting to gush to the surface. There is only frozen ground, rock-hard permafrost, and slabs of ice locked beneath layers of dusty regolith. To turn that ice into usable water is not a single task, but a chain of delicate operations. Drill, heat, capture, store. Each step can fail. All of them must work. Imagine standing on the rust-red plains near the Martian mid-latitudes. The horizon is silent. The sky is thin and pale. Your habitat hums softly in the background. A bubble of Earth air in a world 100 times less dense than our atmosphere. Somewhere under your boots, perhaps a meter down, perhaps 10, lies frozen water. Not in gleaming blue blocks, but as dirty, grainy ice saturated with salts and toxic chemicals, mixed with soil like concrete. To reach it, you must drill. On Mars, drilling is not just about cutting downward. Every meter requires fighting low temperatures, abrasive dust, and a planet that pulls at you with only a third of Earth's gravity. Drill rigs need weight to bite into the ground. On Mars, everything is lighter. Bits chatter. Cores jam. Fine dust infiltrates joints and bearings. Lubricants behave differently in the cold, thin atmosphere. The simple act of penetrating the ground becomes a carefully choreographed struggle against physics. You cannot send a towering terrestrial oil rig. Every kilogram of hardware that lands on Mars has been flung out of Earth's gravity, well at enormous cost. Every bolt, motor, and cable must justify its place. The mass of the drill must be traded against the mass of solar panels or nuclear generators. How much steel is water worth? Assume you reach the ice. Now you must free it. On Earth, ice melts. On Mars, it cheats. At surface pressure less than 1% of Earth's, water does not calmly shift from solid to liquid and then to vapor. For most of the Martian surface, the pressure and temperature conspire so that when ice is warmed, it prefers to skip the liquid phase entirely. It sublimates, jumping directly from solid to gas, like dry ice on a winter's day. Only here, the air is so thin that the escaping vapor is desperate to rush away, out into the near vacuum. Any exposed ice is temporary. Under the open Martian sky, it is a fleeting ghost. If you simply melt the ice in a shallow pit, most of the water will not form a puddle. It will become vapor and drift off, lost. The colony will watch its future drinking supply evaporate into the orange haze. So the extraction cannot be done in the open. You must create a system that drills into the ground, seals around the borehole, heats the subsurface, and captures the vapor as it escapes. Every gram of steam must be shepherded into pipes, condensed, and stored in insulated tanks, protected from refreezing or resublimating. This is not a campfire over a frozen pond. It is industrial-scale cryogenic plumbing, built on a planet that has never known rain. The thermal problem is unforgiving. Mars is cold in a way that penetrates. The average surface temperature hovers around -60 degrees Celsius. The ground itself is a vast heat sink, leaching energy from anything warm. To extract water, you must not only lift ice to 0 degrees, but push it well beyond, overcoming the thermal inertia of rock and regolith. Picture a cubic meter of frozen soil, ice mixed with dust, perhaps 30% water by mass, the rest abrasive grains and salts. To heat this block from -60 degrees to just above freezing demands energy not just to raise the temperature, but to melt the ice within, to break the crystal bonds that lock molecules together. Engineers calculate these budgets with care. Kilojoules per kilogram, watts per square meter, time. The numbers often come back with a quiet message. You will need more power. Solar panels must be large and carefully angled, sweeping across the dust-coated landscape. Nuclear reactors must be small yet robust, delivering steady heat for years. The more water you want per day, the more power you must feed into the ground. And all that power must arrive on rockets, whose payloads are limited and precious. Even if you win the thermal battle, another enemy waits in the ice itself. Mars is not a clean freezer. The ice is not pure. For billions of years, perchlorates, chlorine-rich salts that are toxic to humans and disruptive to thyroid function, have accumulated in the soil. Other salts, sulfates, and fine rock particles are embedded in the frozen matrix. When you warm this mixture, you do not produce crystal-clear water. You release a chemical stew. That means every kilogram of vapor you capture must be filtered, distilled, or otherwise purified. Membranes must be maintained. Filters must be replaced. Distillation columns must be heated yet again, adding to the energy burden. Perchlorates can cling stubbornly to water molecules, refusing to leave without a fight. The system that delivers a glass of safe water is not just a heater. It is an entire chemical plant. To cope with these challenges, engineers have proposed a range of extraction methods, each one a different answer to the same stubborn question. How do you persuade Mars to give up its ice? One concept reaches back to polar engineering on Earth, the Rodriguez Well. In Antarctica, Rodwells are melted cavities in the ice sheet where warm water is injected down a shaft, creating an underground reservoir of liquid that can be pumped up as needed. On Mars, the idea is similar but harsher. Lower a heater into the ice, allow it to melt a bulb-shaped chamber below the surface, and circulate water through a closed loop. The liquid never sees the open air, protected from sublimation by its icy shell. But to sustain such a cavity in the Martian subsurface, you must continually supply heat, fight the relentless urge of the surrounding ice to refreeze, and ensure the cavity walls remain stable in a gravity and temperature regime unlike Earth's. Even the simple task of lowering and raising equipment in a narrow shaft becomes a logistical ballet, performed with robots, far from home. Another approach uses heated augers, long, rotating screws that bore into the ground while their surfaces warm the soil. As the auger churns, it liberates ice that melts, or sublimates within a sealed chamber. Vapor is drawn off, condensed, and stored. The auger must be hard enough to cut rock, yet precise enough to maintain a pressure envelope around the extraction zone. Dust seals, motors, bearings, and heaters all operate at the edge of their design limits, day after Martian day. Microwave extraction offers a more subtle technique. Instead of mechanical drilling alone, high-frequency radio waves are beamed into the subsurface, selectively heating ice and water-bearing minerals. The microwaves penetrate the regolith, causing ice to warm from within, turning into vapor that percolates upward into collection domes. No bits to dull, no mechanical friction to fight. Yet the system must be meticulously tuned. Too little power and the ice remains locked. Too much and the surrounding soil sinters, changing its structure, closing off pathways for vapor to escape. Each of these methods has variants, hybrid designs that combine thermal, mechanical, and electromagnetic tools. All of them share one unromantic constraint: mass. For every extraction unit you send, every drill string, cable reel, microwave emitter, condenser, pump, and tank, there is a ratio that haunts mission planners: mass to water yield. How many kilograms of hardware must land on Mars to produce 1 kilogram of water per day? How long must that system operate before the water it delivers justifies the cost of sending it? Early studies paint a sobering picture. An extraction rig that weighs a metric ton might, under ideal conditions, deliver a few hundred litres of water per day. Factor in downtime, dust storms, wear and tear, and the effective output drops. To support a growing colony, drinking, food production, oxygen generation, industrial processes, you may need dozens of such units. Tens of tons of equipment, all pre-positioned years in advance, each one a little factory in the dust. In the quiet of simulation labs on Earth, engineers run the numbers again and again. They adjust assumptions, they improve designs, they search for efficiencies, but the ratios remain stubborn. To turn Martian ice into reliable daily water is not a single machine problem. It is an infrastructure problem. From orbit, blue hints in spectrometer data may suggest abundance. On the ground, abundance must be translated into flow rates, power curves, maintenance schedules, and spare parts lists. The promise of ice becomes a network of obligations. Drills that cannot fail, heaters that cannot shut down, storage tanks that cannot leak. And yet, in that difficulty lies the shape of a future Mars, if we choose to build it. Not a world saved by a discovered resource, but a world slowly unlocked by layers of engineering. Between the first detection of ice and the first glass of safe, colony-made water, stands a long corridor of problems, all waiting with quiet patience. Beyond that corridor lies another challenge. Even if we can extract the water, what flows into our tanks will not be pure. It will carry the signature of Mars itself, its salts, its toxins, its ancient dust. To drink from this alien well, we must learn not only how to melt ice, but how to cleanse a world. We imagine Martian ice as something simple, clear, silent, waiting patiently beneath the dust for human hands to melt it into drinking water. But as our drills bite into the ground and our heaters begin to glow, we discover something unsettling. Mars did not freeze a mountain stream. It froze a chemistry experiment. Within the pale, dusty ice, a quiet intruder waits, perchlorates. On Earth, perchlorates are niche chemicals. We meet them in rocket fuel, fireworks, and industrial cleaners. On Mars, they are part of the landscape itself. The soil and ice are laced with these reactive salts, woven into the regolith by millions of years of ultraviolet light, splitting apart chlorine-bearing minerals and thin traces of atmospheric gases. Dust storms lift them, radiation drives the reactions, and over time, Mars slowly salts itself. When Phoenix dipped its robotic arm into the high-latitude soil in 2008 and tasted Martian chemistry for the first time, it found perchlorates in abundance. Later missions confirm the pattern. Wherever we look closely at the surface, these salts seem to be there, mixed with the dust, infiltrating the ice. They are not a rare impurity. They are part of the planet's skin. To the eye, perchlorate-laced ice would look ordinary. It would crack, crumble, and melt like any other. But chemically, it is different. In every liter, an invisible cargo of chlorine and oxygen is dissolved, waiting to interact with the most delicate machinery we know, the human body. Perchlorates are masters of subtle disruption. They do not burn on contact. They do not corrode metal like acids. Instead, they slip into one of our most fundamental biological systems, the thyroid. The thyroid gland is a quiet clock at the base of your neck. With iodine as its key ingredient, it shapes hormones that govern metabolism, growth, and brain development. Perchlorate ions resemble the iodine that this gland depends on. So when perchlorates enter the bloodstream, they compete. They block the transporters that pull iodine into the thyroid. The gland starves, not because iodine is absent, but because its doorway is jammed. On a chart, this looks like altered hormone levels, sluggish metabolism, and long-term disruption of endocrine balance. In a growing child, it can mean impaired neurological development. In an adult, it can mean fatigue, mood shifts, and subtle but cumulative health effects. On Earth, we regulate perchlorates in drinking water down to parts per billion. On Mars, raw melted ice could contain concentrations thousands of times higher. A colony, depending on untreated Martian water, would not see dramatic poisoning. It would see something more insidious. Over months and years, health would slowly drift out of equilibrium. Thyroid disorders would become common, pregnancies more complicated. The baseline of normal would shift, and no one would remember when it began. And perchlorates are not alone. Martian geology is ancient and restless. Volcanic eruptions, asteroid impacts, and evaporating seas have left behind a planetary pantry of salts and minerals. When we drill into ice, we also tap into this legacy. Trapped within the frozen matrix are sulfates from long-dried lakes, chloride salts from vanished shorelines, and traces of metals pulled from basaltic rock. Some of these are harmless, some are even useful, but others are quietly dangerous. Heavy metals like lead, arsenic, and cadmium may occur in tiny grains, ready to dissolve into meltwater. Sulfates, benign at low levels, can become corrosive to equipment and irritating to human tissues at high concentrations. Fluorides and other anions might be present at levels that would raise alarms in any terrestrial water treatment plant. Each gram of ice becomes not just H2O, but a complex chemical mixture shaped by 4 billion years of Martian history. To drink from this source safely, a colony cannot simply melt and sip. It must refine. On Earth, water treatment happens off-stage. Filters, resins, membranes, and disinfectants hum quietly in plants and under sinks, invisible to the people they protect. On Mars, none of that infrastructure exists by default. It has to be brought, piece by piece, across millions of kilometers, and fed with precious energy. Purifying perchlorate-rich ice is not a single-step process. Perchlorates are stubborn. They do not easily stick to basic filters. They are small, highly soluble ions that slip through many traditional systems. To remove them, we must think in stages. First, the ice must be melted in a controlled environment. That alone requires heaters, insulated tanks, and careful management of dust and gas release. As the ice becomes water, latent salts dissolve, turning a block of frozen soil into something more like brine. Next, coarse filtration removes particulates, grains of dust, bits of regolith, microscopic shards of rock. This might use sedimentation tanks, mesh filters, or simple centrifugal separation. It cleans the water's appearance, but not its chemistry. Then comes the heart of the process: chemical separation. Researchers imagine using ion exchange resins, sophisticated materials that selectively trap perchlorate ions in their microscopic pores, swapping them for less harmful ions. Over time, these resins saturate and must be regenerated or replaced, demanding yet more chemicals, more equipment, more maintenance. Alternatively, reverse osmosis systems could force water through ultrafine membranes, leaving salts and contaminants behind, but at the cost of high pressures and significant energy consumption. Every litre purified is paid for in electricity, pump wear, and system complexity. For a small research outpost, this might be manageable. For a self-sustaining colony, it becomes a continuous industrial operation. Storage tanks hold untreated meltwater. Treatment modules hum through the Martian's soul, cycling brackish water through filters, resins, and membranes. Sensors constantly monitor conductivity, ion content, and trace metals. Any failure could mean days of rationing while systems are repaired. And even here, at the end of the process, one more step waits: polishing. Activated carbon filters, ultraviolet sterilization, or advanced oxidation systems may be needed to remove organic byproducts, trace oxidants, and microbial contaminants. The result is finally something humans can drink, cook with, and use in hydroponic systems. Clear, safe, and hard-won. Yet in this challenge lies an unexpected possibility. Perchlorates, while toxic to us, are not universally hostile to life. Some Earth microbes have evolved not just to tolerate them, but to use them. Deep in soils, in salt lakes, and in industrial waste streams, certain bacteria breathe perchlorates the way we breathe oxygen. To them, perchlorates are not contaminants, they are energy sources. These microbes strip oxygen from the perchlorate molecules, converting them into harmless chloride ions and, in the process, powering their own metabolism. This strange partnership between life and poison has sparked imaginations. Could we bring such bacteria to Mars? Could bioreactors, seeded with perchlorate-reducing microbes, quietly cleanse Martian water while producing biomass and heat? The idea is simple in outline. Feed contaminated meltwater into a controlled tank, allow bacteria to process the perchlorates, then separate the now clean water from the microbial brew. Such a system would not be trivial. Microbes have temperature ranges, nutrient needs, and sensitivities to radiation and salinity. The bioreactor would need careful control and redundancy, and the output would still pass through additional purification steps. But in a place where every kilogram launched from Earth is precious, using living systems as part of the treatment chain becomes tempting. In concept studies and lab experiments, researchers sketch out multi-stage treatment trains tailored for Mars. First, melt and settle, then mechanical filtration to remove dust. Next, perhaps a biological perchlorate removal stage, followed by ion exchange columns fine-tuned to catch leftover salts. After that, reverse osmosis or nanofiltration to strip out remaining dissolved metals and sulfates. Finally, polishing with UV light and carbon filters. Each stage has its own pumps, valves, sensors, and control software. Each stage has failure modes, maintenance schedules, and spare part needs. Over time, the water plant of a Martian colony begins to resemble a small terrestrial utility scaled to an alien world, humming steadily in the background, turning toxic ice into a lifeline. Standing at the window of such a facility, one might watch a block of regolith-rich ice slowly descending into a melter. Steam curls gently. Pumps start. Quiet vibrations pass through the floor. The process feels more like alchemy than plumbing. Outside, the landscape is dry, dust-laden, and silent. Inside, molecules are being sorted, separated, and transformed, one ion at a time. The myth of Martian ice is that it is a shortcut, a ready-made solution to one of the hardest problems of living away from Earth. The reality is more intricate. The ice is real, abundant in places, and scientifically priceless. But between frozen block and drinking glass lies an entire chain of technology, biology, and energy, an invisible infrastructure that must be designed, launched, assembled, and sustained. In this way, every sip of water on Mars will carry a story, not just of ancient glaciers and buried frost, but of chemistry tamed, contaminants captured, and an environment that does not quite want to be hospitable, yet can be persuaded, with patience and ingenuity, to support life. We like to imagine water as something simple. You dig it up, you melt it, you pour it into a tank, and now you have life in a container. On Earth, this is almost true. Rivers run in the open air. Lakes sit exposed beneath the sky. Our atmosphere quietly does the hard work of holding liquid water in place. Pressure, temperature, and gravity cooperate so seamlessly that we rarely stop to wonder how delicate that balance really is. On Mars, that balance is broken. Step outside on the Martian surface and water does not behave like water. It behaves like a trapped substance, desperate to escape. The atmosphere is so thin, less than 1% of Earth's pressure, that liquid water is not comfortable existing in the open. At temperatures where we would expect a puddle on Earth, on Mars you get something stranger. Water that boils and freezes almost at the same time. This is the pressure problem. On Earth, at sea level, water boils at 100 degrees Celsius. But boiling point is not just about temperature. It is about how hard the surrounding air is pressing down, holding the molecules together. Lower the pressure, and water boils at a cooler and cooler temperature. On Mars, the air presses so lightly that at just a few degrees above freezing, liquid water can start to boil away into vapor. Not violently, not like a rolling pot on a stove, but quietly, persistently, molecule by molecule, drifting off into the thin, red sky. For a Martian colony, this means an uncomfortable truth. You cannot simply store liquid water outside. A tank exposed to the ambient atmosphere becomes a slow leak into space. Cracks, pinholes, microscopic seams, each one is a tiny escape route. Even without a visible rupture, your most precious resource simply disappears. So water on Mars must be kept under pressure. To hold it in a liquid state, you need containers that recreate a little pocket of Earth. Tanks that can withstand the difference between high internal pressure and low external pressure, like spacecraft turned inside out. Domes, cylinders, and bladders reinforced with composite materials, buried under regolith or shielded in rock. Every litre of water becomes not just a fluid, but a structural load. Pipes, too, become more than pipes. On Earth, a water main is a tube in the ground. On Mars, every pipeline is a pressure vessel threading its way through a frozen desert. Valves and joints must be sealed against both leaks and the slow grinding of Mars dust. Any break is not just a spill, it is a flash of water, boiling, freezing, and sublimating into nothing. Then there is the cold. Mars is not merely chilly. It is a world where nightly temperatures can plunge far below the freezing point of water, even near the equator. Any liquid confined in a pipe or a tank must contend with an endless rhythm of freezing and thawing, expanding and contracting, stressing its container like a heartbeat made of ice. On Earth, freeze-thaw cycles crack roads, split rocks, and burst household pipes when winter arrives. We see potholes and broken plumbing and think of it as inconvenience. On Mars, the same process becomes existential. A pipe filled with water that freezes expands with quiet, relentless force. It pushes against its walls, opens microscopic fractures, weakens welds, and slowly erodes trust in the system. A colony relying on long external pipelines would live under the constant threat of this invisible pressure. Every night, as temperatures drop, the water within wants to become ice. Every day, as heat returns, it wants to melt again. Over weeks, months, and years, this cycling can turn even the most carefully engineered infrastructure brittle. The solution is simple to describe and complex to build. Do not let the water freeze. Do not let it boil. Keep it warm. Keep it under pressure. Keep it moving. That means heat. Heated pipes snaking between habitats. Insulated conduits buried beneath the soil. Trace heaters running along valves and junctions like glowing veins just below the surface. Sensors to watch for cold spots, pressure drops, subtle hints that ice is forming somewhere in the network. Even within habitats, water may need to stay inside controlled temperature zones, carefully routed away from cold exterior walls. Each meter of pipe, each junction, each storage vessel carries with it an energy cost. A quiet, continuous drain on whatever power system the colony relies on. Solar arrays softened by dust, nuclear reactors humming in the background, fuel cells murmuring their electrochemical song. Water on Mars is not just something you spend energy to obtain. It is something you must spend energy to keep. Storage tanks do not escape this bargain. Large reservoirs are more thermally stable, but they also represent bigger pressure vessels, greater structural demands, and higher stakes if something goes wrong. The larger the tank, the more careful the design. Reinforcing hoops, layered insulation, pressure relief systems that can vent vapor without losing everything. Some concepts imagine tanks partially filled with ice and topped with liquid, kept at a narrow temperature where the boundary between phases can be managed like a slow, controlled breath. To reduce these challenges, engineers turn their gaze downward. Underground cisterns become one of the most compelling answers. Carved into bedrock or excavated into regolith, then lined with sealants and composites, these buried reservoirs take advantage of Mars's own insulation. A few meters below the surface, temperature swings are gentler. the brutal day-night cycle softens into a steady, colder, but more predictable climate. In these underground spaces, water can be stored behind thick layers of rock that help hold pressure and buffer against radiation. A cistern becomes not just a tank, but a sheltered environment, a cool, stable chamber where liquid can rest with fewer extremes, connected to habitats by short, enclosed, heated links. These reservoirs form the beating heart of a colony's internal water cycle. Inside the habitats themselves, water may live a more comfortable life. Pressurized living spaces allow water to behave more like it does on Earth. Sinks, showers, hydroponic trays, and humidifiers all operate within an envelope of controlled temperature and pressure. Here, water flows, condenses, evaporates, and is captured again in a closed loop that tries to waste nothing. Humidity is monitored. Air scrubbers and condensers pull moisture from breath, sweat, and showers, cycling it back into storage. Inside, the colony becomes a small imitation of Earth's hydrological cycle, scaled down and carefully managed. But every time water must leave that protected bubble, every time it travels from one module to another, from a processing plant to a greenhouse, from a storage cavern to a habitat, those brief journeys must pass through hostile territory. Even a few meters of external routing demands engineering protections, insulation, heating, redundancy, and constant monitoring. The energy cost of this system is not a single number. It is a background reality. Heat must be supplied, pumps must run, sensors and controllers must remain awake. When people imagine Mars colonies supported by abundant ice, they often forget this constant, gentle uphill climb against the planet's environment. The dream is of endless water. The reality is of water on life support. Yet within this challenge, there is also a kind of beauty. Engineers imagine integrated systems where nothing is wasted. Waste heat from reactors or industrial processes warms water lines. Habitat walls double as thermal buffers around storage tanks. Underground greenhouses share their warmth with adjacent cisterns. Some proposals imagine clustering all water-intensive activities, agriculture, life support, manufacturing, within a tightly packed core, minimizing the distances water must travel at all. Others explore more radical ideas, partially melted underground ice layers, serving as in-situ reservoirs. Porous rock formations turned into natural aquifers. Even phase change systems where ice, liquid, and vapor are carefully balanced to reduce mechanical stress on pipes and tanks. Each concept is an attempt to negotiate with Mars, to find a compromise between what the planet offers and what human life requires. In the quiet of a sleeping colony, when pumps hum softly and heaters glow unseen under meters of dust, the water network will be as vital as the air. A hidden circulatory system, always moving, always watched, always demanding attention. Finding ice on Mars may give us hope. Turning that ice into a stable, reliable, liquid water supply is a separate journey, one not measured just in meters of pipe or tons of metal, but in watts of power, degrees of temperature, and years of patient maintenance. On Earth, we take liquid water for granted. On Mars, every drop is a small engineering miracle. On Earth, water feels almost effortless. You turn a handle. Gravity does the rest. Somewhere far away, pumps hum, filters breathe, and treatment plants glow under sodium lights. But for most of us, the energy cost of water is invisible. It arrives as if by magic. On Mars, that illusion vanishes. Every drop is an engineering decision. Every kilogram is an energy budget. And the quiet truth hiding beneath the dream of just use the ice is this: Mars water is not a resource you simply find. It is a resource you must power into existence. To understand why, we step back and look at the full chain, end to end, not as a concept, but as a machine. First, you must know where the ice is and how deep. That means orbiters mapping hydrogen signatures, landers drilling, rovers sampling, radar sweeps, seismic tests, and patient, careful data. Before a single human drinks a single Martian cup of water, vast amounts of energy have already been spent simply to locate trustworthy deposits. Then the real work begins. You excavate or drill through regolith that is more like powdered glass than gentle soil. Machines bite and grind into a frozen mixture of dust, rock, and ice. Excavators must be heated just to keep from freezing solid. Bearings need to resist dust that infiltrates every gap. Motors draw power to dig, claw, and lift in a world where nothing rusts, but everything grinds. The extracted material is hauled to processing units. There, it must be heated above the local temperature, often far below freezing, until ice turns to liquid or vapor. On Mars, that could mean raising a mix sitting at -60 or -80 degrees Celsius up through melting, boiling, and sometimes even beyond to drive off contaminants. Heating dirt and ice is not elegant science. It is brute force thermodynamics. Kilojoules upon kilojoules poured into simple, stubborn matter. On Earth, we can hide this inside industrial plants, powered by massive grids and unseen pipelines. On Mars, it all traces back to a handful of solar panels, a few nuclear reactors, and the faint trickle of radioisotope generators. Once melted or sublimated, the water must be purified. Perchlorates, dissolved salts, metal ions, and possible organic residues all demand removal. That means filters, membranes, ion exchangers, perhaps distillation columns. Each step consumes power. Pumps force water through microscopic pores. Compressors move gases. Control systems monitor and adjust endlessly. Finally, the clean water must be stored, pressurized, kept above freezing, and distributed. Tanks are insulated or heated. Pipes are routed through habitats. Pressure vessels are maintained. Temperature control alone is an ongoing drain of energy because Mars is a world that constantly wants to pull all warmth out of anything that contains it. From scouting to storage, the entire pipeline is a single unbroken energy story. To feel the scale of that story, it helps to compare Mars to places on Earth where water is also hard won. On our world, one of the most energy-intensive ways to get fresh water is through desalination, pulling salt out of seawater. Modern reverse osmosis plants can produce a cubic meter of drinkable water using only a few kilowatt-hours of electricity, roughly the energy to run a small space heater for part of a day. On the coasts of arid countries, massive plants silently turn oceans into faucets, powered by grids that span nations. Go to Antarctica, and you find another challenge. There, water is locked in ice, just as it is on Mars. Research stations must spend energy melting snow and ice, heating it to safe temperatures and treating it. Even so, the energy cost per litre is still manageable, because Earth grants 1,000 invisible subsidies: thick atmosphere, relatively mild temperature ranges, abundant oxygen, and a global supply chain that can deliver fuel and equipment by ship and aircraft. Mars grants none of those. The atmosphere is thin, heat leaks away quickly, and the cold is both relentless and global. There are no existing grids to tap into, no fleets of fuel tankers arriving each year. Where an Antarctic facility relies on external support, a Martian base must bootstrap its own infrastructure from almost nothing. Energy that would be a trivial line item on an Earth-based water budget becomes central on Mars. Producing a litre of water might cost not 2 or 3 times as much energy as on Earth, but an order of magnitude more, once excavation, heating, and extreme thermal losses are included. The exact numbers will depend on future engineering, but the trend is clear. Martian water is closer, in energetic terms, to mining and smelting ore than to opening a tap. This leads naturally to the question, where does that energy come from? The most obvious answer is sunlight. Solar panels are lightweight, proven, and have already powered robotic missions from Spirit and Opportunity to Insight, and the early operation of Perseverance's helicopter companion. But Mars is not a friendly solar farm. Sunlight at Mars is only about half as strong as on Earth. Dust accumulates on panels. Planet-wide dust storms can dim the sun for weeks or months, turning reliable output into a slow, uncertain trickle. Panels must cover larger areas for the same power, be regularly cleaned, protected from abrasion, and supplemented with batteries to smooth the daily night cycle and storm-induced lulls. Solar power on Mars is like living on a diet that is just barely enough, provided nothing goes wrong and you never have to sprint. For a colony that needs to heat regolith, run excavators, melt ice, purify water, maintain life support, and perhaps grow food under artificial light, that is a fragile place to live. So attention turns to nuclear options. Compact fission reactors, like the kilopower concepts tested on Earth, promise steady, day and night energy, indifferent to dust, storms, and seasons. A single small reactor could power critical systems, including water extraction, with a robustness that solar arrays struggle to match. Larger reactors could unlock an entirely different scale of industry. Metal refining, greenhouse lighting, and large-scale fuel production. Radioisotope thermoelectric generators, RTGs. The quiet hearts that have powered missions like Curiosity and Voyager offer another form of nuclear reliability, but at a much smaller scale. They provide heat and a modest trickle of electrical power, useful for keeping systems alive, not for running an energy-hungry water industry. Each of these power sources must reach Mars somehow. That brings us to another hidden cost: mass. Every kilogram of solar panel, battery, reactor shielding, cabling and support structure must be launched out of Earth's gravity well and ferried across interplanetary space. Rockets must burn propellant, stages must be built, and payload capacity must be traded against all the other things a colony needs: habitats, scientific instruments, vehicles, food, and yes, some initial water. An energy system heavy enough to power large-scale water extraction is itself a cargo. The more energy you want, the more mass you must launch. The more mass you launch, the more complex and expensive the mission becomes. In this way, the promise of water is there, just use it, quietly expands into a network of rockets, launch windows, and logistics. And under all these considerations lies a simple but profound knot. Water and energy depend on one another. Most power systems need water in some form. On Earth, power plants use water for cooling, cleaning, and sometimes for the very process of generating electricity. On Mars, even if reactors are air-cooled or rely on radiators, water is still essential for humans to maintain, repair, and live alongside them. For fuel production via electrolysis, splitting water into hydrogen and oxygen, you need water and energy. But that water may depend on the very energy system you are still trying to build. This is the chicken and egg problem of Martian infrastructure. You need energy to get water. You need water to support the people and processes that will maintain and expand your energy systems. Early missions must carry both in tandem: some amount of water from Earth and the hardware to begin extracting more. The balance between what you bring and what you intend to make locally is not just a design choice, it is a survival equation. Engineers and planners use a concept to make sense of these loops. EROI, energy return on investment. On Earth, we speak of EROI for oil wells, wind farms, and solar arrays. How much usable energy do you gain compared to how much you must spend building and operating the system? A healthy civilization rests on energy sources that return far more than they cost. On Mars, we can ask a similar question about water. If you invest a certain amount of energy into mining regolith, heating it, purifying the output, and storing it, how much usable water do you truly get back? Not just in litres, but in what those litres enable: life support, agriculture, fuel. If the energy cost of extracting each unit of water is too high, the system becomes self-limiting. Too much of your available power goes into simply keeping the water loop running, and not enough is left to expand the colony, grow food, or explore. The EROI of Martian water may define the ceiling of how large and how independent a settlement can become, at least in its early centuries. This is the hidden cost of Mars water, not the ice itself, not the drills or the pipes, but the vast, patient machinery of energy that must hum in the background, day and night, to turn frozen minerals into liquid life. When we imagine a future Martian colony, we often picture greenhouses and red vistas, dust storms framing domes under a salmon sky. But perhaps the true heart of that settlement will be somewhere less dramatic. A quiet power unit, humming steadily, feeding a web of cables that disappear into the soil. From that hum, everything else unfolds. Air to breathe, lights to see by, and water that flows not by grace, but by design. Only when we trace the journey of a single Martian drop all the way back to its source in kilowatts and kilograms do we begin to see the full shape of the challenge and the full meaning of the word resource on another world. When people imagine a Mars colony, they picture drills, spinning, grinding, chewing into ancient ice like miners in some rust-red gold rush. Ice becomes the hero of the story. Find enough of it, and everything else will somehow fall into place. But Mars is not a world that yields its treasures easily. And ice is not the only chapter in its water story. If we step back from the romantic image of glistening glaciers buried in dust, another landscape quietly appears. One built not on vast reservoirs but on thin films, trapped molecules, invisible vapor. A landscape of subtlety instead of abundance. Here, water exists not as a single jackpot, but as many small, persistent opportunities. Some of these options are so unassuming that they are often left out of colony plans entirely, and yet they may be the first real lifelines for any settlers who reach the Martian surface. We begin not in the ground, but in the air. Mars is a dry world, but not an empty one. Its atmosphere is tenuous, less than 1% of Earth's surface pressure, and yet every dusk, every night, a quiet transformation unfolds. As the temperature plummets, the thin air cools, and the relative humidity can climb. Near the surface, especially in certain regions and seasons, the night air can become surprisingly humid by Martian standards. Not a tropical rainforest, but a cold, ghostly mist of opportunity. On Earth, engineers have already learned how to pull water from desert air using special materials that cling to water molecules, like microscopic nets. On Mars, similar sorbent materials, or advanced metal organic frameworks, could sit out under the fading light. As night deepens and humidity rises, they would begin to drink from the sky, trapping water vapor molecule by molecule. Then, as the pale morning sun returns, Those materials could be gently warmed by solar panels or waste heat, releasing their captured water into small condensers. No drilling, no excavating, just a nightly rhythm. Absorb, release, collect. A slow inhalation and exhalation of the Martian atmosphere. This method will not fill rivers or reservoirs, but it does not need to. Early outposts will be small, their crews few. A network of quiet, patient devices stretched across the regolith could gather litres per day. Not dramatic, but steady. A water income layered on top of other strategies. And in a world where every gram counts, a trickle can be as important as a flood. Beneath this fragile atmosphere, Mars holds another, less obvious store of water. Not as ice, but as chemistry. Scattered across the planet are minerals that formed in the presence of water. Clays, sulfates, perchlorates. Many of these minerals are not just evidence of a wetter past. They still carry water within them, locked into their crystal structures as what scientists call structural or bound water. Imagine a grain of Martian dust. It looks inert, lifeless, meaningless. But heat it carefully in an oven, and at certain temperatures, that grain begins to change. The crystal lattice reshapes. The bonds loosen. And water, once part of the rock itself, is released as vapor. On Mars, this chemistry could be turned into a quiet industry. Regolith, rich in hydrated minerals, would be scooped up and fed into thermal processing units. Inside, carefully controlled heat would coax water out without melting the rock entirely. The steam would be captured, condensed, purified. What was once a dusty hillside could become, over months and years, a source of liquid life. The trade-off is clear. The hydrated minerals do not give up as much water, gram for gram, as pure ice. More material must be processed, more energy spent per litre. But in return, this approach offers something precious: flexibility. Hydrated minerals exist in more equatorial regions, where sunlight is stronger, where landing is easier, where temperatures are less brutal. The colony, in turn, is not chained to the cold, ice-rich mid-latitudes. It can follow the sun. There is another path, even more abstract, yet surprisingly powerful. A path that begins not with water, but with its ingredients. Water is hydrogen and oxygen, bound in a simple, elegant ratio. Mars offers one of these elements in overwhelming abundance. Its atmosphere is almost entirely carbon dioxide, carbon and oxygen, floating just above the surface. With electricity and the right chemistry, that oxygen can be freed, separated from the carbon, turned into a breathable gas, a source of oxidizer, a component of future rocket fuel. But hydrogen is another story. Mars has some, but not nearly enough in accessible form for large-scale industrial use. So one proposal sidesteps the problem entirely. Bring the hydrogen with you. Hydrogen, the lightest element in the universe, is also the lightest cargo. Whether stored as cryogenic liquid, compressed gas, or bound up in hydrogen-rich compounds like methane or ammonia, it represents a concentrated potential. Once on Mars, this imported hydrogen could meet Martian oxygen in carefully controlled reactors. Combine them, and water appears as a product, not a resource to be mined. In this approach, a colony is not just a consumer of local materials. It becomes an alchemist, reconstructing water from the most fundamental parts. The advantage is clarity. No dust contamination, no buried surprises. The chemistry is well understood. The engineering is challenging, but already explored in life support research and rocket design. Yet, as elegant as it sounds, this method carries its own invisible cost. Every kilogram of hydrogen imported is a kilogram launched against Earth's gravity push through space, guided to a safe landing. Each drop of water made this way has a launch history, a trail of energy spent long before it ever touches Martian soil. Because of that cost, every litre will be guarded closely. And that leads us to the most essential and perhaps least glamorous water source of all, the water we already have. On the International Space Station, astronauts live inside one of the most advanced water systems ever built. Their water is recycled through a near-closed loop. Humidity from breath, sweat from exercise, urine, even condensed moisture from the air, all gathered, filtered, and purified. Up there, yesterday's coffee can quietly become tomorrow's tea. Modern closed-loop systems can recover well over 90% of the water used. Some designs push close to 98% under ideal conditions. On Mars, such efficiency will transform water from a consumable into a circulating medium. The same molecules will pass from glass to greenhouse, from food to fuel cell, from skin to air and back again, tracing a cycle more like a small artificial ocean than a simple tank. Recycling does not eliminate the need for new water entirely. There will always be losses, small leaks, vented gases, chemical locks into materials, but it dramatically reduces the amount that must be mined, manufactured, or imported. In the arithmetic of survival, recycling turns an impossible demand into a manageable one. And so we arrive at the most controversial, and in some ways, the most honest option, to keep sending water from Earth. It feels like a step backward. After all the dreams of planetary self-sufficiency, the image of cargo ships quietly unloading tanks of water at a Martian habitat seems almost disappointing. But for the earliest missions, this may be the most reliable backup humanity can offer. Mass is expensive to launch, but risk is more expensive still. In the fragile first years of a colony, failures will happen. Drills might seize in unexpected layers of rock. Atmospheric harvesters could clog with dust. Reactors may fall short of their promised yields. During that time, having a stream of supply missions, each carrying not only equipment but also water reserves, could mean the difference between a setback and an ending. Over time, this resupply would be expected to shrink, then become emergency only, a safety net beneath increasingly capable local systems. But in the beginning, it may form one leg of a tripod. Imported water, harvested water, recycled water, each supporting the others until the colony can truly stand. When we compare all these options, ice extraction, atmospheric harvesting, hydrated minerals, imported hydrogen, closed-loop recycling, resupply from Earth, the numbers blur into the same language: energy and mass. Ice may seem free, but the drills, heaters, purifiers, and storage tanks are not. Hydrated minerals trade depth for volume, requiring more rock to be processed for each litre of water. Atmospheric systems sip gently at the sky, but must run constantly, using pumps, compressors, and heaters that demand steady power. Imported hydrogen spares the need for digging, but every kilogram requires a towering launch, a rocket's roar, and a long, patient journey through space. Even recycling, the quiet champion, has its own costs. Filters must be replaced, pumps maintained, membranes monitored. The system must run without pause because the colony's survival is woven through its pipes. In the end, there is no single perfect answer, no hidden shortcut. Mars will not offer us an easy spring bubbling beside the landing site. Instead, it presents a mosaic of partial solutions, each with strengths and weaknesses, each demanding energy, technology, and time. The myth of Martian ice imagines a world where one discovery solves everything. The reality is more intricate and in many ways more beautiful. Water on Mars will not be found. It will be managed, cultivated, recycled, built, drawn from air, rock, chemistry, and the silent reservoirs of space itself. And in that careful balancing act, between extraction and import, between scarcity and circulation, we begin to glimpse what a real, living Mars colony might look like. Not a frontier powered by a single miraculous resource, but a fragile, resilient system where every drop has a story and every choice has a cost. When we talk about Mars colonies, timelines are often measured in launch windows and presidential terms. 2029, 2033, 1 million people in 20 years. Numbers spoken with the confidence of a flight schedule, as if booking a ticket to another continent rather than another world. But water does not follow press conferences, and ice does not care about roadmaps. If we overlay the quiet, stubborn reality of Martian water onto the bold timelines of SpaceX, NASA, and other agencies, the picture changes. Not into impossibility, but into something slower, more layered, more patient than the slogans suggest. SpaceX speaks of building a city. NASA speaks of a sustained human presence. Other nations and private companies sketch out bases, labs, and habitats scattered across the red plains. On paper, these futures have landing dates. In practice, they have preconditions. And at the top of that list, written in invisible ink, is water. In the earliest missions, Mars will not be a place where we live off the land. It will be a place where we carry our life with us, sealed inside metal and plastic. Every liter accounted for, every drop watched. The first crews that step onto Martian soil will not be miners. They will be caretakers of a closed loop. Their water will arrive not as ice chunks carved from the ground, but in tanks tucked inside landers. In food, in fuel, in the very air they breathe. They will recycle it through careful systems, much like those on the International Space Station. Vapor from their breath, moisture from their sweat, water from their urine, all cycled and recycled in a steady, invisible orbit within their habitat walls. Experiments with local ice will happen, yes, but not as grand industrial operations. At first, they will be more like field tests than factories. A small drill sinking into the regolith near a promising patch of ground. A heated probe melting a tiny volume of ice, maybe just enough to fill a beaker. Sensors watching how dust behaves, how pipes clog, how machinery fares in the cold and the perchlorates. These first attempts will not water cities, they will water data. Mission timelines that promise in situ resource utilization often compress a multi-decade engineering journey into a bullet point. Yet if we listen more closely to the people who design the systems, the story stretches out. Before Mars can host a water plant, it will host prototypes. Not one, but many, each with a different way of digging, heating, filtering, storing, each learning a new lesson in how alien the familiar substance becomes on another world. On Earth, developing a new industrial process can take 10 to 20 years. On Mars, where every repair is delayed by light minutes of distance and months between launches, that timeline elongates. Systems must not only work, they must almost never fail. They must shrug off dust storms, temperature swings, and the silent abrasion of time. Imagine the development path as a long, slow staircase. At the first step, early missions carry all their water, relying on recycling to stretch supplies. Mars itself is a backdrop, not yet a source. On the second step, robotic precursors land dedicated water extraction experiments. Small-scale drills, microwaves that heat subsurface layers, tiny reactors that process melted ice. Their goal is not production, but understanding. How does ice behave at different depths? How fast does equipment degrade? Where does contamination creep in? The third step comes when humans and machines work together. Crews tend to slightly larger systems. Maybe they produce tens of litres per day, enough to top up reserves, to supplement, to build confidence. The water they make is precious not only for survival, but as proof. A demonstration that the numbers in engineering papers can become real, cold, drinkable liquid. Only later, much later, do we reach the wide steppes where output is measured in tons per year, where a settlement's air, fuel, and agriculture begin to rely primarily on local water rather than earthly shipments. To get there, we are not counting in launch windows anymore. We are counting in generations of technology, under optimistic scenarios, with consistent funding, repeated missions, and a run of good luck. Some researchers imagine industrial-scale extraction in perhaps 30 to 50 years after the first crews arrive. Under more cautious assessments, that horizon stretches further, toward the end of the century. And yet, the people who study Mars most closely are often neither cynics nor cheerleaders. They live in a space between. Many planetary scientists and engineers will tell you a permanent self-sustaining Mars colony is not forbidden by physics. The planet has water, it has carbon dioxide, it has minerals, metals, regolith that can become bricks and radiation shielding. The ingredients are there. But they will also tell you that self-sustaining is not a date you can write on a calendar. It is a slope, a long one. At first, everything depends on Earth, spare parts, complex electronics, medical supplies, high-value foods, and yes, most of the water. Over time, if we are persistent, that dependency shrinks. A fraction of the plastics are made locally. Some metals are refined on site. Greenhouses expand. Ice extraction systems grow, fail, are redesigned, grow again. Mars researchers tend to think in phases rather than slogans. Reconnaissance, outposts, bases, then maybe, someday, something we might honestly call a colony. Water threads through all of these stages like a quiet condition. How much can we bring? How much can we recycle? How much can we reliably pull from beneath our feet? Optimistic timelines imagine that within a decade or two of the first human landing, Mars could support hundreds, then thousands, of residents using local resources. Under certain narrow assumptions, rapid launch cadences, breakthroughs in automation, robust nuclear or solar power, and an unusually smooth development curve, this is not impossible. But each of those assumptions is its own mountain. Power systems must be both abundant and unrelenting to melt ice on the scale of a community. Logistics chains between planets must be dependable for years at a time, surviving political and economic changes on Earth. Robots must operate almost like a workforce, building and maintaining hardware with minimal human intervention. And the environment itself must not surprise us with some hidden complication buried in the dust or the deep ice. When engineers fold these uncertainties into their calculations, the picture shifts from cities in 20 years to settlements that slowly harden from fragile outposts into robust habitats over many decades. This is not a failure of vision. It is the shape of reality asserting itself. Yet timelines that lengthen do not necessarily dreams that fade. They often do something more subtle. They force our creativity to deepen. The difficulty of Martian water may shape the way we approach space settlement everywhere. To solve these problems, we may need closed-loop life support so efficient that a glass of water can trace 1,000 invisible cycles through air, plants, and people before being lost. Mining technologies that can operate for years in extreme cold without human hands to clear a jam or wipe a lens. Lightweight, modular purification systems that can handle any mixture of salts, clays, and toxic chemistry for use not only on Mars, but on the Moon, on asteroids, and in disaster zones on Earth. Energy systems that are less vulnerable to dust and night, be it compact nuclear reactors or solar infrastructure designed to clean and repair itself. In this way, the ice that refuses to yield easily becomes a teacher rather than an obstacle. It forces us to learn how to live within tight ecological boundaries. It pushes us toward robustness instead of quick fixes. It nudges our technologies toward forms that could help not just Martians of the future, but people on Earth today. So when we revisit the bold timelines with all of this in mind, they do not simply collapse, they transform. A human landing in the 2030s or 2040s may still be within reach. The first research habitats, heavily supplied from Earth, could follow. A small network of outposts connected by data and occasional cargo flights might grow slowly across the decades. The dream of a thriving Mars colony does not vanish. It stretches. It steps out of the shadow of marketing and into the longer light of engineering and planetary time. Water, in this story, is not a magic key that suddenly unlocks a city the day we detect it. It is the long, quiet test that runs in the background of everything we do there. A test of patience, a test of design, a test of how far we are willing to go and how long we are willing to wait to turn a hostile desert world into a place where a child might one day wake up, look out at the dusty horizon, and think of it not as an expedition, but as home. We have followed the ice down into the shadows of Martian craters, buried it beneath dust and rock, weighed it against energy budgets and engineering limits. Now we slowly rise back up, above numbers and diagrams, into the quieter question that waits behind all of it. Why did we ever think it would be easy? The story of water on Mars did not appear by accident. It was shaped, edited, and repeated, the way light is scattered through Saturn's rings. Each time it passed through a new lens, newsrooms, mission press releases, hopeful animations of future colonies, it became simpler, brighter, more certain. In the early days, the headlines were careful. Evidence of past water. Possible subsurface ice. Over time, that caution eroded. Water found on Mars became Mars has water, and then, somewhere along the way, that turned into an unspoken promise. We've solved the hardest part of living there. Space agencies and scientists rarely say this outright. They speak in probabilities, in models, in caveats wrapped around their data. But between careful words and public imagination, a gap opens. It is in that gap that myths grow. Part of this is practical. Exploration needs funding. Missions need approval. Legislators and the public are more likely to support a future they can picture. Clear ice, melted into drinking water, fueling rockets and greenhouses beneath a salmon-coloured sky. It is easier to tell a story with a single bright word, water, than with a paragraph of conditions. Perchlorates, dust storms, cryogenic plumbing, energy deficits. This simplification is not usually malicious, it is translation. The cosmos is written in equations, the audience hears in headlines. Somewhere between those two languages, complexity is lost. There is also something deeply human at work. Space is not just a place, it is a mirror. When we look at Mars, we are also looking at ourselves, our hunger to expand, our fear of scarcity, our curiosity, our wish for a second chance written across another world. Mars has water does not only mean Mars has ice. It whispers something softer. Maybe there is room for us out there. For more than a century, Mars has been a canvas for our imagination, first with canals and dying civilizations, then with microbes in rusted soil, and now with domes of glass glinting on the horizon. Each generation paints its own dream over the same cold desert. Water is one of our oldest symbols of hope. On Earth, where there is water, there is life. Where there is water, there is a future. When we learn there is ice on Mars, it lights up the same circuits in our minds. We leap ahead, skipping the machinery, the equations, the brutal arithmetic of energy and mass. In our imagination, the ice is already in a cup, already filling a habitat tank, already turning wheels in a hydroponic garden. Myths like this are powerful. They pull students into science, inspire engineers to design new systems, push agencies to send new missions. Inspiration is not a small thing. Entire careers begin with a single simplified image in a schoolbook, or a breathtaking animation of a future Martian city. But myths also bend our expectations. When we believe that Mars has water means Mars will be easy, we set ourselves up for a different kind of gravity, disappointment. Technical setbacks feel like betrayal instead of progress. Realistic timelines look like pessimism instead of planning. Hard-earned incremental advances are overshadowed by the absence of miracles. The truth is quieter, but far more interesting. Challenges do not mean impossible. They mean intricate. Extracting water from toxic, dusty, deeply buried ice on a freezing world with thin air and frequent storms is not a wall we cannot pass. It is a maze we do not yet fully understand. It asks us to think differently about energy, about redundancy, about failure modes in a place where a cracked pipe is more than an inconvenience. When we let go of the comforting myth that water on Mars equals problem solved, we make room for something better, honest optimism. Honest optimism does not say, it will be easy. It says, it will be hard, and we will try anyway. This shift in attitude changes the kinds of questions we ask. Instead of, when do we move in? We begin to ask, what would it truly take? How many kilowatts for each litre of water? How do we repair equipment in abrasive dust? What happens when a drill gets stuck 100 meters below the surface? How much redundancy is enough when resupply is months away? These questions are not the enemies of dreams, they are their guardians. Each one answered on paper, in simulations, in small-scale tests on Earth, removes a hidden failure from the future. History is full of moments when the world looked at a frontier and quietly declared it impossible, or at least unbearably difficult. For centuries, humans sailed close to coastlines, unwilling to lose sight of land. The open ocean was a rumour, a blank space on maps. Crossing it safely required more than courage. It needed new ship designs, better navigation, a deeper understanding of winds and currents. The myth of endless deadly ocean was not wrong, it was incomplete. When we learned its patterns, when we respected its scale and its storms, the Atlantic did not shrink, but it became traversable. Flying heavier than air machines once sounded as fanciful as domes on Mars. Early attempts ended in broken wings and discouraging crashes. The dream of flight remained, but only when engineers stopped imagining wings as flapping bird replicas and embraced aerodynamics, material science, and engine power did flight shift from a myth to an industry. The sky did not become less vast. We simply met it on its own terms. Even space itself began as a story more romantic than real. Simple posters showing rockets escaping Earth's gravity skipped over the subtlety of orbital mechanics, the careful sideways fall that makes a satellite circle instead of crash. The myth was a straight arrow leaving the planet. The reality was a dance around it. Once we understood that dance, the impossible became routine. Mars will follow the same pattern. Today, we stand in the early chapters, where images and slogans outpace engineering. The water on Mars myth is an invitation, not a conclusion. It has done its work in capturing our attention. Now it must step aside for a more detailed map. An honest assessment of difficulty does not cool the dream. It refines it. When we admit that Martian water is locked behind layers of dust, salt, toxicity, and distance, we start to think in better directions. Closed-loop life support systems that waste nothing, ultra-efficient power sources, manufacturing that works with local materials instead of shipping everything from Earth. We begin to place Mars in context, not as a quick escape hatch from Earth, but as a long-term project in planetary adaptation and patience. This change in perspective also turns our gaze back home. The same technologies needed to conserve, recycle, and carefully manage water on Mars are useful on Earth, where climate, infrastructure, and population put increasing pressure on our own supplies. The myth says, ice on Mars will save any colony. Reality answers, no, but the effort to make it usable might teach us how to save ourselves. As we drift above this red world in our imagination, the details of drilling rigs and intake valves begin to fade into the background. What remains is the shape of the challenge itself, vast, intricate, but not unknowable. To balance dreams with engineering reality is not to dampen wonder. It is to root wonder in something that can endure. The day a human drinks a glass of water entirely harvested and purified from Martian ice, it will not feel like the fulfillment of an old headline. It will feel like the culmination of thousands of careful, unglamorous decisions. Between myth and reality lies the work. In that space, we are not just passengers of grand narratives about easy water and inevitable colonies. We are participants in a slower, more deliberate unfolding, where every honest constraint we face becomes a stepping stone rather than a stumbling block. Mars will not welcome us because it has ice. If we go, and if we stay, it will be because we learn to see past the myth, to accept the full weight of the challenge, and to move forward anyway, patiently, precisely, and with our eyes fully open. As our journey across the Martian deserts comes to a close, we find ourselves looking down at a world that is both familiar and utterly alien. We have traced the promise of ice from polar caps to buried glaciers, from crater shadows to ancient riverbeds. Along the way, the simple story we were told, there's water ice on Mars, so colonies are just around the corner, has dissolved into something more complex, more challenging, and in many ways more beautiful. The geography refused to cooperate. The safest landing zones and the richest ice deposits rarely overlapped. The ice itself hid beneath layers of stubborn regolith, demanding machines we have not yet built, and energy systems we have not yet launched. The water, once freed, revealed its own quiet dangers, salts, perchlorate, and dust that must be tamed before a single sip is safe to drink. Then came the silent accountants of reality: storage, transport, power, and maintenance, reminding us that every litre of water on Mars will be earned, not given. And yet, none of this is a verdict against Mars. It is a map. To see the obstacles clearly is not to abandon the dream, but to finally put it on solid ground. Every engineering nightmare we explored is also a research program waiting to be funded, a student's thesis waiting to be written, a future invention waiting in the dark between ideas and reality. Problems, once named, become solvable. Myths, once examined, become plans. There is a quiet kind of courage in choosing truth over comfort. It would be easier to imagine Mars as a frontier where ice lies at our feet. ready to be scooped up like snow from a winter field. But science asks us to do something gentler and more demanding, to sit with the real numbers, the harsh constraints, and the long timelines, and still say, yes, this is worth it. Honest science does not dim the stars, it sharpens them. It replaces the blur of wishful thinking with a clearer, steadier light. When we admit that building a self-sustaining colony on Mars is not a project of years, but of decades, perhaps generations, we are not surrendering ambition. We are aligning it with the scale of planetary time. Somewhere in the future, machines will bite into Martian soil and draw water from the deep. Reactors or vast fields of solar panels will hum quietly in the thin red air. Habitats will recycle every molecule they can, turning waste into resource, scarcity into resilience. The first true Martian colonists may never see Earth's oceans again, but they will live because we chose to ask hard questions now, instead of later. Between dreams and reality lies the work. Tonight, we have simply traced its outline. If you've stayed with this exploration of Mars water all the way to the end, thank you. Your curiosity is part of the same quiet force that sends probes to distant worlds and turns vague hopes into careful designs. If you'd like to help this journey continue, you can gently tap like, leave a comment, and subscribe. Let us know where in the world, or perhaps which time of night, you're listening from. And if you want to support us a little more directly, there's an optional YouTube membership you can join, but only if it feels right for you. For now, let Mars rest in the darkness, its hidden ice locked in ancient cold. The planet is not waiting for us. It simply is. We are the ones learning to wait, to prepare, and to understand. Some night, far ahead, someone may stand beneath a pale pink sky, drink water drawn from Martian stone, and look up. When they do, they will be living in the world that began with questions like these, and with nights like this one. Sleep well, and keep wondering.